Fantastic. Well, hello again, everyone. My name is Chris Doran. I am a technical sales specialist for Global Test Supply. Thank you for joining us for our webinar today, brought to you by Global Test Supply University. Today's topic is how ground testing keeps us safe, presented by Megger. Throughout the presentation, we're going to ask you to mute your microphone. Presentation should last about 45 minutes or so, and we will have a lot of time at the end of the presentation for Q&A. We are going to encourage you to try and get any and all questions that you may have in throughout the presentation. You see a slide that triggers something, please use the chat feature, get your question in, and we should have some time to get to a few of them by the end. Global Test Supply and Megger have been working closely together for many years. We pride ourselves on being a leading distributor of Megger in the US, and this is a result of our dedication of offering you our product expertise, our service, and our competitive pricing. Today's webinar is presented by Jeff Jowett. He is a senior applications engineer with 40 years of instrumentation experience and the last 20 or so in marketing and distribution sales. Jeff has written numerous trade journal articles, conducted training for distributor sales as well as customers, and has been a speaker at various electrical societies, including the NETA and NJATC, pardon me. Jeff, I will turn the presentation over to you.
Okay, thank you very much. And thank you everyone for attending today's talk on grounding, ground testing, and a grounding system. And so we're going to look then at why you want to ground your electrical system, the benefits you get out of it, why it's something you do not want to neglect, and we'll look at how to do the testing, and we'll look at some of the instrumentation that's involved, and the general schematics of how the instrumentation works, because it's an enormous benefit if you're operating out in the field to actually know what the tester is doing and how it's making its measurement, because unlike a lot of other types of equipment, there's a lot of operator involvement in doing a grounding test. DMMs and things like that, you know, a lot of times it's fairly simple to hook up a couple of leads and get a measurement. But on ground testing, it's considerably more complex, and the variables can be difficult to deal with. And so if you understand the schematic and how it works, you'll be good to go, and you'll be able to address problems in the field. Okay, a quick introductory look here at why we're doing this. What are the benefits of having a good grounding system, grounding your electrical facility? And of course, probably the first thing that people think about when they with respect to grounding is lightning strikes. They're pretty dramatic. In certain areas of the country, they do occur quite frequently and can cause a lot of damage. You could be in an area where you don't get much lightning if you're lucky, but most of the country they do. And so a good grounding system will divert lightning out of your building, and that's the idea behind it. Divert it out of your building and send it to ground where it's harmless. Similarly, fault currents, they behave very much similar to lightning. The utility has a problem, something occurs on the utility, causes a fault current, and then that current in turn is trying to find its way to ground. You want it to go through a grounding electrode. You don't want it to go through your equipment. And most important, you don't want it to go through a human being, because bear in mind, if a voltage gradient develops somewhere across your equipment, and the human happens to get in touch with that, the human could become the best path to ground. And so you definitely want to eliminate any possibilities of that by having a good parallel grounding system. And then there's also, we mentioned static charges, especially in certain environments, manufacturing, where you have things like belts, machinery running with belts. they very often will separate charge. You'll get a static, you'll get a negative side and a positive side, and then that will build up, and then at some point, if it gets high enough, it'll discharge itself, and you don't want it discharging through equipment. You want it to find its way into a grounding system. And then another thing to mention is very significant and becoming more and more so all the time as there's more computer controlled operations and things of that sort, is noise. What is, a voltage signal that doesn't mean anything to an electric light can look like an X or an O to a computer system, and so you want to, for those systems to manufacture to operate at maximum efficiency, you do want to eliminate noise from your electrical equipment, and especially the more sensitive stuff, computer and process control and things like that. And your grounding system is key in removing that noise from the electrical system. As we said, of course, injury, that's really the most fundamental and the most important benefit of having a good ground. That there's no place in your electrical facility where someone is going to touch something and get shocked. And so you want to make sure that everything is in place, not only your grounding electrode, but also your grounding conductors. You want to make sure that all your conductors are in place from equipment down to your ground bus, a very low impedance path, so that a human body doesn't look like a good current path by comparison. And we mentioned lightning, and we mentioned computer and communication. So all very important elements in a grounding system. And so you want to kind of think of your grounding system in an expanded sense. It's not just that rod that's buried outside in the soil that extends up like tree branches or whatever through your entire electrical system. Okay, so we're going to start looking at the theory, and there's very interesting theory behind ground testing. Some electrical test functions are fairly simple, but ground testing has a certain degree of complexity to it that makes it kind of interesting. And there are two fundamental types of measurement, and that is resistivity and resistance. And today we're going to look at both resistivity and resistance. They sound very much alike. They're frequently confused. And so you do want to be careful in cases where you're having a dialogue with any kind of a third party, an inspector, a client, anyone like that. You want to make sure, and I'll come back to this several times, you want to make sure that your terminology, you're on the same base with respect to your terminology. So resistivity, that is an independent electrical property of the soil itself. Soil is actually a relatively good conductor, primarily because there's so much of it. If it's not restricted in some way, a current, it's not like going through a wire and the gauge of the wire tells the current about what it can do. But in the soil, the current can wander pretty much wherever it wants to go, and consequently, it makes a pretty good ground in that regard. But the electrical properties of the soil are critical in grounding your electrical system, and we will talk about those. And then there's resistance, which is a different function. It's a different measurement and a different type of test. And resistance is now when you've grounded your system and you got your ground rod in place, you want to be able to test it. Just driving a rod into the ground isn't enough. It could be if you're lucky, but you don't want to place such high stakes on luck. So you want to make sure that you actually have a really good ground. and that's where your resistance measurement comes in, and we will cover that as well. So we'll start with earth resistivity. And so a couple of things you can do here. A resistivity measurement, if you have an option for, a spot of land that you can work in, you find the lowest resistivity, that would be a good place, if you're trying to put up a tower or something like that. It could be useful in that regard. Find the lowest resistivity spot, and that's where you will have your best protection. And then also, it's information that goes into how to design a grounding system. The resistivity, in turn, is based on numerous variables, of which the earth composition, the moisture in the ground, and the temperature are all very important. And I'll touch back on those from time to time. Certain types of soil, like loam, are pretty good grounding materials. They have good electrical continuity through the soil, and they make a good grounding material. And other types of, like sand, is pretty bad. So if you're in an environment that's sandy, you're going to have more of a challenge getting a good ground than somebody who I guess is up in the Iowa farmland or someplace like that. And then moisture is critical because, of course, the water in the soil is promoting current flow. And so dry soil doesn't promote current as well as moist soil. And so the average moisture content is important, but also the moisture content around the calendar is very important. You want to keep that in mind because you don't want, in most areas, the best times of year are spring and fall in general. Winter and summer tend to be the more demanding times. So you don't want to have a ground that meets spec, no problem in the spring, and then you have a hot, dry summer, and it goes out of spec, and something happens and you lose equipment. So you want to be careful of that. And then, of course, temperature itself is very important, has an effect upon the soil as well. So as we said, it'll vary throughout the year, and it'll vary with the amount of moisture. And then that bottom note there, depending on where you are, if you have you may have an issue with the frost line. So just be aware if you're up in a northern clime somewhere, maybe if you're up in Maine, a place like that, you probably have frost line issues. And you always want to make sure that your ground is below the frost line. If you install it too shallow, then it has the same effect as a frozen car battery. Same general idea. Ice doesn't conduct current, and water does. So if you all of a sudden you install a ground in relatively good weather, and then a dead of winter sets in, and it's a bad winter or whatever, and you're shallow buried, you could basically have no ground anymore until the spring thaw. So especially if you're in that kind of environment, some places you don't need to care about it, but if you're in that kind of environment, keep that in mind. So now we're going to take a look here at the technology and the theory behind doing a resistivity test. So this is how you would test the soil on your site and determine what kind of resistivity you have. And this is a basic schematic of a 4-terminal tester. And I think probably some of you have already recognized that this is a Kelvin bridge, which is also used in a number of other types of electrical test instrumentation besides just grounding. And what it does, you got 2 current terminals that are on the outside, and they inject a test current. And in the case of ground testing, it will be a square wave because you want to avoid the noise that's in the soil. And it can be a surprising amount. All the stuff that got chopped up and dumped back into the soil from computer processing and things like that. That's all trying to find its way back where it came from. And so that'll interfere with your measurement if you don't have a good noise tolerant tester. And so the tester looks for its own signal and it ignores everything else. And then between your potential probes, they're in the middle, they sense the voltage drop. And so note this, the tester injects the current. It knows how much current it was able to put into the ground. It measures the voltage drop between those two internal pins, and it tells the measurement module, and then that gives you your resistance measurement, which is the resistance of actually the letter A here, which is in this case the resistance between those two internal pins. That's what the tester is actually looking at. And that's equivalent to a depth of A. And so if you want to measure 15 feet down, you space your probes 15 feet and so forth. And that's basically how it operates. And then that gives you a number up on the display. Okay. And now this I should mention, this is Wenner method. It's very common. You'll see it in the literature all the time, invented by a guy named Frank Wenner in the early 20th century. I think he was from the U.S. Geological Survey, I believe. Don't know for sure. But there are other methods that use, they're not hugely different, but they tend to use different spacing sometimes for operator convenience. So you will see other methods in the literature, but Wenner is by far the most commonly used method. And so here's some more comments on it. We kind of discussed what the parameters are. So I think that's all pretty obvious. And then note what you want to do at the bottom here. Note you have this little formula, 2 pi AR. So resistivity is a volumetric measurement because current can spread out anywhere 360 degrees in the soil. So it's not like wire gauge where it's a constant. So instead, it's a volumetric measurement. So the units of measurement of resistivity are typically in ohm centimeters. Now, if it's more convenient for you, you can use ohm inches or ohm feet if you want. But industry standard is ohm centimeters. So you would take your R, that's your reading off your display on the tester, and then of course your A is your spacing, and you plug that into that formula, and that would give you your resistivity to a depth equivalent to A in ohm centimeters. And oh yeah, and then another thing I wanted to mention on that is that 1/20th that you see there. Now, if you were strictly by the Wenner method, it requests that you drag the probes in 1/20th of the distance that they're horizontally spaced. And so you'll see that in the literature a lot. It's not that critical from conversations I've had with testing services, for instance. So if you're trying to measure a shallow depth and you're trying to put your probes in 1/20th and they barely hold, then don't worry about it. Just, drive them in enough so you get a measurement. There'll be a certain amount of error that will be introduced, but it's typically not critical. And so, don't space the whole success of your method on just using a 1/20th depth on your probes. Okay. And note also you can do something else here by mathematical manipulation. You can also manipulate your terms and calculate out what your electrode resistance ought to be. Okay, now we'll take a look at the other measurement, which we mentioned, which is resistance. And here we switch from the soil itself. Oh yeah, there was one other thing I did want to mention. Now that I think of it, about the soil, about soil resistivity, and many of you may be interested in this, and that's how do you go about establishing you've done your resistivity. Now, what do you do to meet your ground? And there's two ways that are commonly done. One of them is drive and test. So you can drive your rods deeper, or you can add more rods, and you keep testing until you get there, till you get the number that you want on your resistance. Now, there's nothing wrong with that, and it's commonly done. The one drawback to it is the increments become smaller and smaller, and so the testing can become tedious after a point. So another way to address that would be to go to a grounding company and get a software. And I think the companies that make your ground rods and your grids and all the different materials that go into a ground, I think they'll typically provide you with a software. And then you put the software in a computer and you can tell the software what you want, which of course would include the resistivity measurement. You'd have to have that in there. You would tell it what your ground resistance, what you want it to be. I'm trying to get a 5 ohm ground, for instance. And then it'll design it for you. And it'll make a little schematic and it'll show you need 20 10-foot rods, or whatever it happens to be. So that's another way to address grounding your system if you're faced with that task. Okay, now you've done that, and now the next thing becomes, okay, what about testing it after it's in? Well, unfortunately, a common thing in this industry with respect to grounding is out of sight, out of mind. So the idea is very commonly held incorrectly that all you got to do is just drive a ground rod and hook your electrical system to it and you're good to go. Well, that's not true. First of all, it may not be adequate in the first place. But even if it is, a lot of things happen to that, even though you can't see it. The rods erode away underground, they rust, they erode in other manners. Fault clearance and very energetic faults and lightning strikes and things like that, they can clear perfectly well. There's no damage up to your building. You think, hey, everything went great. And it did, except that now the grounding electrode is not in the same condition it was before it cleared the fault, because they can self-destruct in the process of clearing a fault. So you want to be able to test your ground to make sure that you meet spec when you install it, and then test it periodically thereafter to make sure that nothing is happening to it and that it's not eroding away or being damaged in some other manner. So simple thing, of course, would be your single driven ground rod. Complex systems can become very complex. You have quarter-acre grids. Sometimes solar, it's even more than that because the fields become so large. So with respect to that, to keep it in focus, an electrode is an electrode, and that's it. It's a piece of metal in the ground to create an electrical interface between your electrical system and the surrounding soil. So the only reason, instead of a 6-foot rod, you're putting in a 20-foot grid is to just get more metal in the ground. That's really what it's doing. There are some little features in addition to that that are of some significance, but that's the main object that you're aiming towards. And testing them is pretty much the same. You're testing a single ground rod or you're testing a whole grid. They test pretty much the same, with the one major caveat being, which we will see shortly, is that a large electrode, you know, a rectangular grid or something like that, can require a lot more room, a lot more space to perform the test. But the test itself is fundamentally the same as if you were just testing a single ground rod that is a building ground. Okay, so we kind of looked at why you want to do this. And these are some additional functions. You want to make sure that you have a good low ground so that your protective devices will clear properly. You'll have some people will tell you, oh, well, the utility grounded neutral is doing that. Well, yeah, it is, but that's not the sole component. The grounding system is a parallel backup to that, and so it's a good idea to have your grounding system in place and operating well. Ground potential rises. We'll talk about them as we go along, and then we'll take a look at things like step potential, touch potential, and some other factors of that nature. Figuring ground potential rise. In other words, you don't want voltage rise anywhere in your building across your equipment or across personnel, and that's what you're trying to eliminate. So speaking of personnel, here's a most fundamental test. Now, this is done primarily at substations, but if you're in a big industrial facility, maybe have on-site generation or something like that, this could also be relevant, possibly. This is step and touch potentials. And what these are, it's a way of measuring what the maximum voltage a human could be subject to in the event that a fault clearance is in progress. So note here, what happens if somebody walking by were to touch the fence, and it's while the substation is in effect clearing a fault somewhere out on the line. Well, that current is flowing back to the substation through the earth. And so, so your touch potential would be a person touching the fence. Step potential would be the voltage that can develop between your feet, or about 3 feet. So the way you do that, you take a 4-terminal tester, you test, you make one current connection to the electrical grid, the grounding grid. You make your other current connection remotely. It's not real critical. That's C that you see there. That's just a probe that the operator drives in the ground some distance away. And then the potential probes, you're going to have one of them connected up to the fence, and the other one that's your P probe, which is in the ground about 3 feet away from the fence. So that's your touch potential. And then your step potential will just be 2 probes about 3 feet apart, like we see B and A there. And so what you're doing is you're measuring the resistance that would be between the parameters of someone touching the fence, and their foot is maybe 3 feet away from the fence or something like that, and someone walking by in 3-foot strides. And so you take the resistance measurement off your tester, and you would get the maximum fault current that substation can experience. And if you multiply them out in simple Ohm's law to give the voltage, you don't want the voltage to be any less than 50 volts. And I think it varies somewhat in different jurisdictions. So you may want to look at what the what the edict is in your particular region. I think some places it might be 40 volts. But the idea is that an injurious voltage will not develop across that person's body or between their feet. And if it's less than 50 volts, that's generally regarded as safe or not injurious. So that's your step and touch potentials. And what what that's doing, as we just see here, it's just guarding against ground potential rise, which can occur because the currents, which were previously spread out through an enormous amount of soil, as they approach the substation or the source, the grounded transformer, whatever it happens to be, then of course the field narrows down, and these currents are flowing to, instead of spreading out, they have to channel down into the substation grid or whatever, it's seeking its return. And so that's where you get ground potential rise, and that can be certainly very dangerous, and you do want to make sure that you're guarded and protected against it. Okay, give me just a moment, and now we'll take a look at the components of a grounding electrode. And this is a simple representation here, but it applies the same with any electrode. You have the resistance of the rod, and this could be the resistance of the quarter-acre grid. It's pretty much, the same factor. Then you have the contact resistance with the surrounding soil, and you have the resistance of the surrounding soil itself. And number 1 and 2 could be surprising, but they don't amount to very much. The rod is a big metallic mass, so it's not contributing anything critical. You might think the contact resistance would be a problem. It can be in difficult soils. So keep it in the back of your mind. If you're in sandy or rocky soil, there is the possibility that contact resistance could be a problem because there's a lot of air gap in there. It may sound stupid, but if you talk to anybody who's a soil expert or whatever, there's actually air around every little grain of sand, and that impedes the flow of current. So sandy soil is bad, rocky soil is bad. You may want to allow for that. But for the most part, most of what you're concerned with is just the ability of the surrounding soil to conduct your current safely away from your electrical system. And we kind of show spheres, what we call spheres of influence. In other words, the further you get away, the critical thing to remember here, the further you get away, this is not like the gauge of a wire that stays the same. This gets bigger and bigger as you go further away. So consequently, law of diminishing returns, eventually it becomes zero. At some point, you're so far away that any additional soil is not contributing anything significant. So it's the soil that's impacted around your electrode that's important. And that's what you're going to want to measure. Okay, so now we're going to look at a couple of the different methods here. The 2-pole, we'll start with the 2-pole. We'll do flow potential. We'll look at, I don't think we actually have slope method in this presentation, but I will touch on it. And then we'll look at art, and we'll look at stakeless measurements. And we begin with, okay, we're going to do a ground resistance measurement. That's going to give us a number. So what? Well, in the US, and I'm sure probably a lot of you have already heard this, 25 ohms or less. That's the only prevailing code that goes across the whole nation. And that's from the National Electric Code, but it's very forgiving. And the code itself will tell you that. The code doesn't really concern itself with how well your equipment functions, with whether your computers are going offline from noise. The code doesn't care about that. The code doesn't want buildings catching fire and people getting shocked. And so the code is relatively forgiving in that manner. So yeah, a 25 ohm ground, that's kind of like your drop dead number, but it isn't really a good number for effective industrial and commercial grounding. So in general, now there is no other prevailing national authority. It is often a good idea to have an authority, especially if you're preparing reports for a client or someone like that. But if you do want to cite some sort of authority, then look at your industry. Different industries like nuclear, for instance, they're going to tell you how they want their nuclear facilities grounded and so forth. So look at your industry, look at relevant authorities, and you can get numbers if you want to put it in a report that says such and such an authority said that this facility needs to be grounded at 3 ohms, no more than 3 ohms. So you can, and you've got 2.5, and so, you know, everything looks good. So in general, the most common parameter is 5 ohms for industrial and commercial. A forgiving parameter is about 10 ohms, and you'll see that some people will allow that. But in general, probably the best one is 5 ohms. And then if you get into more demanding environments, computer room ground, for instance, chemical plant, substations for the utility, there the demands become stricter and the numbers get lower. And so substations, yeah, a lot of times they want them grounded at less than an ohm. Okay, so we'll start with looking at the simplest way to do this, and this is the dead earth or 2-pole method. And this is using a ground tester very similar to the way you would use a DMM, which is to say you take 2 leads and you hook them from here to there and you make the measurement in between. So essentially that's what you're doing. You're reducing the tester to a 2-pole configuration. You can do that by shunting them together. In the old days, you shunted the poles together. The newer testers have selector switch positions for every combination. And then you're going to run a lead out to some convenient return point. And so what is very often used in this situation would be the water pipe system because it's pervasive and it's metal, so it should contribute relatively little to your reading. And so the idea then is when you energize the tester, the test current is going to travel through the soil over to the water pipe system and then return through your leads. And it's going to tell the tester what the series loop resistance of that entire loop is. And what you're relying on is that the soil around your electrode is what's contributing nearly all of that number. And that the return path through the water pipe system, where you may have used a long metal fence post, for instance, sometimes you could use that. But you got to hope that that's contributing very little to your measurement. So your number is going to be a little bit high, but not too bad. Now, this is basically what you would call a cheap and dirty type of test. Why would you want to do it at all? Well, a couple things. First of all, it is cited in ieee 81, which is the ground testing standard. So if you want to cite an authority, if you want to tell a client, this is the best I could do, and you know, it might be okay. And then the other parameter here is it's mainly used in very crowded environments, urban type environments, where you just don't have any room to work, which we will see on the next couple of slides why you do. But if you just don't have, you're totally buffaloed, you just don't have anywhere that you can go with running probes out into the soil, you can do a 2-point test, find a convenient return, and do a 2-point test. And it's a drop-dead test. It's better than nothing. And that's the extent of it. But it's important to know about it. So, you know, this pretty much is self-explanatory. It shows you that there are some problems with it. And I guess it didn't really show us any thumbs up. But if we did want to put a thumbs up in there, it would be that it's what you use when you just have no other option. Put it that way. Okay, so now we'll look at three-pole full potential. This is the most fundamental, most accurate, most reliable means of doing a ground test. And in this case, you have a three-terminal tester. I could have mentioned also with respect to doing soil resistivity. Ground testers come in 3-terminal and 4-terminal models. If you're going to do soil resistivity, you must have a 4-terminal model, and we saw why, because we showed you that little diagram which required 4 terminals. A 3-terminal tester can do resistance just fine, but it can't do resistivity, so keep that in mind. So now in a resistance test, you're going to connect your tester to your ground, of course, and then you're going to run a current probe out generally as far as you can conveniently get it. The idea is you want it to be out of your way, and we'll show you why in a couple of slides. And then your potential probe, you're going to move that in intervals out towards the direction of your current probe, and you're going to take a series of readings. It's going to measure the resistance of A on this diagram. What is the resistance to the place you put your current probe, your potential probe, excuse me. And so I think on the next slide, if we can show that. Okay, this just kind of summarizes a little bit what we're doing here, and you're going to plot a graph. That's key to the success of this function. So note here, this is your layout. You've got the broken lines there indicate an electrical field. The electrical field does not really, well, theoretically it goes forever, but in a practical sense, fortunately, it does not go forever. The electrical field is a finite area of soil around your ground rod. And it can be relatively large if you're in bad soil. It can be relatively small if you're in good soil, whatever. But bear in mind that your current probe also has an electrical field around it as well. And we'll see what the significance of that is in a moment. So now, this is what you're going to result. You're going to graph this distance with resistance, and you're going to look for where that line flattens out. And if that line flattens out at like 8 ohms, and you're supposed to meet a 5 ohm ground, you've got to drive more rods. If it flattens out at 2.5 ohms, you're good. Back up and you're good for now. So this is the way it works then. You're taking a series of readings and you're plotting them just like we see here. And you look for you look for this graph at the end. It's the full potential graph. And let's see, note here, we say usually 62%. So if this current probe was out at 100 feet, then your best reading is probably going to be at 62 feet. So the scope of this 1 hour talk can't go into all of that. It's fairly complex, but you can look it up in the literature if you're interested. But at any rate, just know that it's based on ideality. So in other words, yes, if all the conditions were ideal, then the 62% would be where you would have your most accurate reading. The problem with it is, suppose there's a water main running under there. Suppose there's an electrified cable running under there. That's going to influence your measurement. So you don't want to rely on 62% unless it's a backup measurement at a site that you're already familiar with. But for your initial test, you want to do the full graph and make sure that you've got a good measurement. And here's why. Oops, wait a minute. Oh, okay. I will touch on this for just a moment, then I'll show you why. You will see in the table, okay, so the next question is, well, how far out do I want to run my current probe? Well, you'll see in the literature, you'll see tables that give you a distance to your current probe based on the dimension of your test ground. The best thing to remember about those tables is that they are suggestions. They're there to give you a pretty good chance of not having to repeat the test. They're not ironclad scientific. So if the table tells you to go out 500 feet and you don't have 500 feet, go out 300 feet. And if you get a good fall of potential graph, you're good. Don't worry about it. So, and we'll show you, I think the next slide. Yeah, this shows you why. This shows you why. Because the current probe has its own electrical field. And if that overlaps with the electrical field that you're trying to measure, then it fogs the clarity of your graphics and you can't reach a conclusion as to where is the actual resistance measurement of your test ground. And that's the reason for it. So you're not done. If you are in this kind of situation, there are other methods. And one of them, the most common one, is called slope method. We don't go into that in this 1 hour talk, but it's available. And if anybody's interested in it, you can certainly contact me and I'll get it over to you. But this is your most fundamental method. And then if this doesn't work, and usually the reason it won't work is because you can't get your current probe out far enough, then there are alternatives you can go to, which we don't discuss here, but I'll be glad to tell you about. So this is a summary then of the good side of fall potential. It's the IEEE method, and it's highly accurate and highly reliable. On the other hand, it's a lot of work, and it is time-consuming and labor-intensive. Okay. So now we can look quickly at simplified fall potential. This is where you don't want to spend quite as much time. So now, instead of moving your probe a whole bunch of times, you only take 3 measurements, half the distance, and then you move in 10% and you move out 10%. So you got 3 numbers instead of 10 or 20 of them. And you see over on the left, there's a simple mathematical equation that you plug those numbers into. And what that calculates out is your percentage accuracy. So the average of those 3 numbers will be your correct number within a certain percentage accuracy, just like you get on any DMM. So if you have a good, a 1% or 2% accuracy, you're fine. If you've got like a 10% accuracy, you're probably not going to be too happy with that. So you would try it again. And so that's your simplified fall potential. Okay, and then we got 2 more technologies to take a quick look at. One that we call art method. Now, if you're on a new site, then you don't have to worry about art method. But if you're on a site that's connected back to the utility, it's being fed by the utility, then if you run a ground test, you're going to get a good reading, except it's going to be the reading of your ground in parallel with the utility ground that's feeding your site. And that's not what you're really concerned about. You want to know what your ground reading is. So in the old days, you used to have to break the utility connection, which is, not easy and not a good idea in many instances. But now with art method, you get a special tester that has a built-in current clamp. And you clamp that around either your ground rod or your grounding conductor, but you clamp it downstream of your alligator clip. And now this is going to measure how much of your test current returns by your own on-site ground. And that's where it's going to base its measurement. And it's going to ignore what goes back through your utility ground that you don't care about. So that's your ART method, and that's a good way to be able to test grounds that are already installed, but you don't want to lift them. Okay, and then we have ClampOn, and in this method, you have ClampOn ground testers that actually have two windings in the jaws. They look like a ClampOn ammeter, but actually they have two windings, both current and voltage. And so you clamp over your ground rod, and what happens is it inductively establishes a test current on your ground rod that will travel through the soil, and it will seek out its own return, which usually will be the grounded utility. So it's working similar to the dead earth method does, except that the utility is generally grounded at a very small number, and so it's contributing a lot less. Still reads a little bit high, but generally not by very much. So where it's applicable, the ClampOn method is really good to use. It's quick. You're out of there in a hurry. The main drawbacks to it are shorts and opens. If you have a short, that would be if your grounding electrode is connected to the electrical system at more than one point, which a lot of them are. And if that happens, then your test current is going to just travel around to all those other ground connections and loop back, and you'll get a beautiful low reading, and it's wrong because it's only telling you what the continuity of the metal is. So you can't use it there. And the other thing is an open, which would be basically a new ground that hasn't been connected to the utility. There's no return path for the current to come back and give you a measurement, and the tester will show you as an open circuit. People do sometimes jury rig temporary returns so they can do this. There's really nothing wrong with that, except that it does kind of defeat the purpose of having a ClampOn in the first place. So those are your two advanced technologies, ART and ClampOn. And the last thing we're going to take a look at then, and this is just real quick, just the idea of substation testing is particularly demanding because of the noise problem. Worse than just about anywhere else. In our catalog that you see on the left there, the Det2 III, that has enhanced noise suppression capabilities. It does continuous noise graphing, so you can see what the background was at the time that your measurement was actually posted. It has high and low test currents. You can adjust your test frequency to try to find the most quiet frequency, and it also has filtering. So just keep that in mind. If you're testing these types of environments, very, very noisy, you could walk away. Well, you could either not get a measurement at all, or you could possibly walk away with an incorrect one. So make sure you get a high noise capability tester. And then another considerable problem, especially with a big structure like this, is the distance that it takes to run your probes out. In the old days, that could be a real problem. They would get wire anywhere they could and string it out and then have to wrap it back up and all of that kind of thing. But in our catalog now, we have these reels that can be daisy chained. So you can buy as much wire as you need and very simply daisy chain them together and stretch them out. And even for seemingly prohibitive test distances, you can still do it. And with that, I think we have reached the end of the presentation, except for if there's any time left for questions.
Thank you
for your attendance and your attentiveness.
Thank you very much, Jeff. Yes, we do have a few minutes to take your questions, so please use the chat feature. If we don't have a chance to get to them during the presentation, we will contact you privately and individually on a question-to-question basis. So please use the chat feature. If you do have any questions related to specific pricing, specific products, recommendations, suggestions for your potential applications, please go to our website, globaltestsupply.com. On the contact us page, you can find all our contact info, our email address, our phone number, as well as the ability to connect with a live agent as well. We did have a couple questions come in. One from Randy. How does wetting the probe or wet soil affect the test results?
Chris, I'm sorry, you gotta run that by me again. Webbing?
So how would wetting the probe, the ground probe, or how would wet soil affect the test results?
Yeah, very good. One of the most, to the point questions anybody could ask. You can wet the probes. The test probes are not part of the measurement, but they do have to meet a certain parameter. Now, the parameter is quite high. I mean, on our testers, it's up in thousands of ohms. But nonetheless, the probes do have to make enough contact with the surrounding soil to make their measurement. And so to do that, yes, you can most certainly wet them, and that's an effective technique. It does not affect the measurement. However, wetting the ground that you're testing will drastically affect the measurement, or it can. So, to inject a little comedy here, if you want to fool the inspector who's coming today or something like that, and you want to throw water on your ground, it's not a good practice, of course, and we don't advocate that. But that's what would happen if you wet down your test ground and then perform the test. You'd get a low reading. But then, of course, when it dries out, you might be losing equipment up in your building, so it's not a good idea. But the inquirer was quite correct on that. Wetting the ground will lower the resistance, and so the way of dealing with that, basically, industry standard is if you're doing maintenance testing, and you're every so often you go out and you run a test. Well, do it at odd intervals, 7 months, 9 months, something like that, because then your different tests will fall around the calendar, and you'll see when it's worse than other times, and you want to make sure that you meet spec at your worst possible time, which is probably going to be dead of summer, like August, or dead of winter.
Fantastic. Well, thank you very much, Jeff. To respect everyone's time, we have reached the end of our hour, so we will cut off the Q&A portion at that point. We did get a few more in, so as mentioned earlier, we will get in touch with the people that did send in questions individually via email. It'll either be myself or one of our technical sales staff will contact you to answer the question that you have. So Jeff, once again, thank you very much for the presentation. A lot of information covered. If any of you have any questions after the webinar, please visit our website or contact us page to get in touch with us. So on behalf of Global Test Supply University, thank you very much for attending today. We hope you found it informative and helpful. We are able to assist you in any way that we possibly can. Once again, globaltestsupply.com. You'll find our entire list of Megger products, pricing, availability, rental options, as well as all of our contact info to get in touch with one of our technical sales staff. At the end of this webinar, in just a couple minutes, you will be prompted to complete a short survey. We do ask you to take the time to complete it. This will help improve these webinars and bring you subjects down the line that are of interest to you as well. Speaking of upcoming webinars and subjects, we do have upcoming webinars over the next week, over the next weeks and months. On the training section of globaltestsupply.com, you can find the list of dates and subjects for upcoming webinars, as well as don't forget that as a thank you for participating in today's webinar, your name will go into a draw to win $100 for your next online purchase. The winner will be announced on our social media channel, so please be sure to check us out there. Once again, Jeff, thank you very much for the presentation. Thank you all for joining us today. Wishing you a great rest of the day.